This is Math 1090, Section 1.3, Rates of Change in Behavior of Graphs. First, the definitions. The average rate of change describes how the output quantity changes in relation to the input quantity. The units on a rate of change are output units per input units. And we have a formula here for the average rate of change. It's just the ratio of the change of output to the change of input. Or we often summarize this by saying delta y over delta x, where delta is the capital Greek letter for the capital Greek letter delta. And we use delta because it sounds like the D in difference. So whenever you hear or see a delta in mathematics, it always is going to represent some difference between two quantities. Why a difference? Because the difference is how we measure change. Okay, you take the difference between two y values, and that's how much y has changed. The difference in two x values, and that gives you how much x has changed. Okay, and then you take that ratio of change, and it gives you some valuable information. We'll see plenty of examples today. So marginal cost, this is a special kind of rate of change. All of the marginals are special kinds of rates of change. Marginal cost describes the change in total cost if the quantity of items produced increases by 1. Marginal revenue is very similar. It describes the change in revenue if the quantity of items produced increases by 1. And finally, marginal profit describes the change in profit if the quantity of items produced increases by 1. Really, all of these definitions should increase the quantity of items produced and sold, typically. But okay, so those are the definitions. Here's an exercise. The following table gives the daily receipts in millions of dollars for the movie Star Wars: The Rise of Skywalker. Find the average rate of change of the daily receipts from day 35 to day 119. Include units and interpret the result. Okay, so I'm going to use the average rate of change formula, which I will summarize as just being given by delta y divided by delta x. Okay, or in other words, y2 minus y1 over x sub 2 minus x sub 1. And our first point is the receipts for day 35. So this will be our x column. This is the x column. This is the y column. So we'll call 35 x sub 1, and then this 10,814,000, that's going to be y sub 1. And then the second day we care about is day 119, so we'll call this x sub 2, and this will be y sub 2. So then y sub 2 minus y sub 1 is going to be 0.182 minus 10.814, all divided by x2, 119, minus x1, 35. All right. So we have 0.182 minus 10.814 for a difference of negative 10.632. And then 119 minus 35, I could probably do that in my head, but the calculator's handy. So 119 minus 35, that's a difference of 84. 10.632, make that negative and divide it by 84. There we go. negative 0.127. Let me just check that. Okay, so now we are asked to interpret and include units on this. So we want to understand what this number represents. Well, remember that average rate of change is always going to take the units of the output variable divided by the units of the input variable. So our output variable is receipts in sales of tickets, right, in millions of dollars. So it's millions of dollars per day. Okay, so that's what this means. So now if I were to take this 0.0127 and multiply it by 1,000,000, well, that's the same as moving the decimal place over to the right 6 places. So this is equal to negative, let's see, I'm just going to do 1, 2, 7, and then 2 more decimal places, then put my comma in the right place. So 1, 2, 3, 4, 5, 6. All right, and then the units of the input variable are days. So then what does this mean? This is the average rate of change. So on average, from days 35 to day 119, the average rate of change per day was they lost, or they went down $12,700 in ticket sales every single day over that 84-day span, is what that means. Okay. Okay, next example. The table below gives the annual sales in millions of a product. Determine the average rate of change from 1998 to 2002 and also from 2002 to 2006. Which period saw a larger rate of increase in sales? Okay, so we have another table. Our sales function is given to us as a table of data. And we'll call the year will be the input variable, and the sales related to that year will be the output variable. So let's call this x1, and then this will be y sub 1. And then year 2002, we'll call this point 2, so we'll use x sub 2 and y sub 2. So we have 2 points that we're comparing, and we want to compute the average sales over that time period. So that's going to be change in y divided by change in x, or delta y divided by delta x, which is going to be y2 minus y1. So that's 377 minus 233 divided by x2 minus x1, so that's going to be 2002 minus 1998. And I think I'll just use the calculator again here. 377 minus 233 is 144. So we get 144 in the numerator, and the denominator, that's a difference of 4. So we get 144 divided by 4, which is going to be 16. Okay, so what are the units on this? This is the units of the y variable are going to be sales, or millions of dollars. The units of the denominator variable, or the x variable, are years. So this is an increase of $16 million in sales per year. So 16 million per year increase in sales. Okay, what about the period from 2002 to 2006? Well, we're going to compute delta y divided by delta x again. But now, what's x1 and x2 and y1 and y2 will change. So let's call the younger, we'll call this point 1, the corresponding to the year 2002, and the year corresponding to 2006 we'll call point 2. So this will be x1 and this will be y1 now, and this will be x sub 2 and this will be y sub 2 now. So we want to do y sub 2 minus y sub 1, so we're going to do 329 minus 377 divided by x2, which is 2006, minus x1, which is 2002. All right, 329 minus 377. Let's see, 329 minus 377. Hold on. Is negative 48. The denominator is that's a difference of 4. So this is negative 12. So during this period of time, on average, the company lost 12 million per year. So the years 2006 to 2002 were not good years on average for this company. But notice, for example, from 2002 to 2003, their sales actually increased. So that was a good year. But on average, over the whole span of 4 years, sales decreased by 12 million per year. So not good over the whole span of 4 years. Okay, let's do the next exercise. The table below gives the rental pricing in 3 cities in 2009 and in 2015. Which saw a larger rate of change? Include units in your response. Okay. So we have rents in Boise, Boston, and Seattle for the years 2009 and 2015. So I think what we want to do is create a average rate of change for each city. So over here, I'll do the computation for Boise. Here, I'll do the computation for Boston. And over here, I'll do the computation for Seattle. Okay, so we're thinking here as the rent as a function of the year. So my y values will be rent, the cost in rent. My x values will be the year. Okay, so let's see. In 2000, let's see, my first rent for, sorry, my second rent. So this will be our Y1 column. Let me just move that down just a little bit. This will be our Y2 column. So the change in Boise rent, it went from 583 to 745. So we do 745 minus 583 to find the difference. We always subtract we always start with the most recent value and subtract the previous value when dealing with time. And then the time periods were 2015 for the higher rent and 2009 for the lower rent. So let's see, what is this? This is going to be, I'll use the calculator again. 745 minus 583 minus 583 is 162. So 162 over, let's see, 2015 minus 2009 is a difference of 6 years, of course. So we have 162 divided by 6. Well, I'm getting in dummy calculator mode. 27. Okay. So this is equal to the units of the numerator are the units of rent, which is dollars. The units of the denominator are years. So this is going to be $27 per year. So we have an increase of, on average, $27 per year in the Boise region. Next, let's do the same thing for Boston. R delta Y over delta X. So our change in Y, our most recent rent in Boston is $2,150. And then the rent before that in Boston was $1,577. Again, this is over the same span from 2015 to 2000, starting in 2009. And let's use the calculator again. 2,150 minus 1,577. 2,150 minus 1,577. That's a difference of 573. So divided by 6, 95.5. So in the Boston area, rent changed from 2009 to 2015 by an average of $95.5 per year. So remember, this is just an average. Some years it could have gone up more, other years it might have gone up less. For all we know, there could have been some years where rent stayed the same or even went down. But on average, it increased by $95.50 per year. Okay, now let's do the same calculation for Seattle. So we want to compute delta Y over delta X. Let's see, for Seattle we want to do 1,600 minus 958 over the same difference in years. Let's see, 1,600 minus 958. Oh, well, I'll use the calculator. 1,600 minus 958, $642. So 642 divided by 6. It's 107. Okay, so what does this mean? It means that on average, In the Seattle area, rents went up by $107 per year during that time period. Okay, our next exercise has a graph. Looks like it's relating the price of gas to the date, the day of the year for Salt Lake City. And they're taking prices of regular gasoline over an 18-month span of time. Okay, using the 18-month average retail in Salt Lake City, Utah, find the following. The average rate of change of gas prices from February 26, 2019 to May 12, 2019. Okay, so again, this is another average rate of change problem. So we're going to be computing the change in y divided by the change in x. Okay, so let's see here. I put some points on the graph. You'll see. So we'll call this date 1 because it comes before this date 2. So May 12, 2019, the price was what? Well, if we go on the graph and we look at this point right here, it looks to me to be about 3.14, maybe 0.05 shy of 3.19. So that would be 3.14. Maybe write that down. $3.14 per gallon on that date. And then in February 26th, that's this point right down here, 2019, that would have been, it looks to me like about, let's see, 0.15 minus 0.03, that's a difference of 0.12, so it's maybe a quarter of the way up or so, maybe a little less. So I'm going to say 2.05, so $2.05 per gallon on February 26th. All right, so the dates are the x values, the prices are the y values, right? Because we have price over here and we have day on the horizontal axis. So we always take the more recent y value, and that was $3.14 per gallon. We subtract off the $2.05 per gallon gasoline. And now we've got to compute a difference in these days. Okay, May 12th, 2019. It turns out that the calculator on Windows can do this pretty well. So if you click here on that little hamburger menu thing, you see there's a date calculation feature. We want to go from February 26, 2019 to May 12, 2019. Okay. So February 26th, 2019 to May 12th, 2019. There we go. It's a difference of 2 months, 2 weeks, and 2 days, or 75 days. You can see it says it right here at the very bottom. 75 days. Okay. So our denominator is 75. Okay, 3.14 minus 2.05. We want to go back into regular scientific mode. 3.14 minus 2.05 is $1.09. And $1.09 divided by 75 is about 0.01453 repeating. So we have 1.09 divided by 75 is equal to 0.01453 repeating. Okay. All right, we want to do the same thing, but now our dates change to May 12th, 2019 to July 27th, 2019. So July 27th, 2019, so that's this date down here. So that's this point on the graph, which corresponds with what price of gasoline? Let's see, 2.84 minus 2.73, that's 0.11 units in between. So I'm going to say that's about 0.04 units up from 2.73. So 2.73 plus 0.04 is 2.77. So we want to do 2.77 minus the $3.14 on May 12th. And we need to calculate the change in date as well here. So this is going to be starting from May 12th, 2019 to July 27th, 2019. So let's switch this to date mode. Our first date is going to be May 12th, and then we want to go to July 27th, 2019. So that's apparently 76 days. Okay, so 2.77 minus 3.14. 2.77 minus 3.14 is a difference of negative 37 cents. So we get negative 0.37 divided by 76, which is divided by 76. It's about negative 0.0049. Or, so let's interpret both of these. So this is from February to May, the price of gasoline increased by a little over a penny per day. Whereas for the 76 days between May 12th and July 27th, the price of gasoline decreased by almost half a penny per day. All right. So in business, the average rate of change is related to the idea of marginal cost, marginal revenue, and marginal profit. It is usually defined as the change in cost or revenue or profit when the quantity of items produced and sold increases by exactly 1. This is a very useful idea in business. It tells you how much, marginal cost is going to tell you, well, at this production level, how much is it costing me to produce one more unit? Or at this production level, how much more revenue will I take in for every unit sold? Or at this production level, how much more profit will I generate for every unit produced and sold? Okay, so it's the same exact idea as average rate of change, except now we're always putting some dollar value in the numerator, and the denominator is always going to be 1, because the difference when you're producing your production increases by 1 unit is going to be 1. So, and this is closely related to concepts from calculus. Calculus is the study of change, and the techniques of calculus allow you to study how a function changes at an instantaneous point in time. And we're basically doing the same thing here with marginal cost. Okay, it is a measure of how the cost of production changes, not as a function of time, but as it changes with quantity produced. So we see here in the graph, though, so you see the idea here is that we're taking the change in, this is our change in y right here, and this length, the base of this right triangle, is going to be our change in x. So we're taking the ratio of change in y to change in x, and what is it? It's going to give us the slope of that line. Okay, so slope and marginals are closely related, and differentiation and slope are closely related in calculus. Okay, so a company has determined that the total cost of producing Q items is given by this function C of Q. Find the marginal cost when production is currently 5,000 items. Okay, so what we want to do is take the outputs of the function when producing 5,001 items and the output of the function when producing 5,000 items, take that difference and divide it by 1. So we just need the difference. So the marginal cost is going to equal the cost of producing 5,001 items minus the cost of producing 5,000 items. So we just need to evaluate the cost function at 2 different values. So the cost of producing 5,001 items is going to be 2,000 plus 50 times the square root of 5,001. The cost of producing 5,000 is going to be 2,000 plus 50 times the square root of 5,000. Okay, now this simplifies. This expression simplifies. Notice the constant term in the function 2,000. Well, we have positive 2,000 on the left, but we have negative 2,000 on the right, so those cancel out. And all we're left with is this 50 times the square root of 5,001 minus 50 times the square root of 5,000, which I'm going to rewrite as 50. I'm going to factor 50 out. I'm going to write like that. Okay, and now it's calculator time. let me clear this garbage out and clear that. So we'll need to use parentheses this time. We want to do 50 times parentheses 5001 square rooted minus 5,000 square rooted. And now I need to close those parentheses. And there we go. You see the expression I'm trying to evaluate is up at the top of the calculator window there. And it results in 0.00700707 and some change. Okay. So what does this mean? This means that when I produce 5,000 items, what does it cost me to produce the next item? Well, this is dollars per item. So this is, it's about $0.007 per item. So less than a penny. It costs me less than a penny to create the 5,001st product. So very cheap product. Okay. And of course that will change at different production levels. The marginal cost, the cost to produce one more item, changes depending upon how many you produce. Typically, when you produce in volume, in greater quantities, the costs go down. So the cost to produce one more item will be less and less and less as you produce more and more and more, because you're able to use high volume production typically results in scaling down of costs. Okay. Here we have a similar exercise. The cost of producing X stuffed buffalo toys is given by this cost function. Find the marginal cost at the production level of 1,000 stuffed buffalo toys. So again, our marginal cost is going to be the difference in cost of producing the 1,001st item minus the cost of producing the 1,000th item. Okay, and this is going to be given by, I'll put this in brackets, 0.0003 times 1,001 squared plus 6 times 1,001 plus 7,000 minus the cost of producing 1,000 items. And I'll put that in brackets as well. 0.003, oops, 3 zeros there, so 0.0003 times 1,000 squared plus 6 times 1,000 plus 7,000. Okay, similar to before, these constant terms, 7,000, any time you do this, the constant terms of your functions will cancel. And I can simplify. So this is going to be 0.003, sorry, I did it again, 0.0003 times 1,001 squared minus 1,000 squared plus 6 times 1,001 minus 1,000. So this simplifies a little bit. Let's see, we're left with 0.0003 times 1,001 squared. I don't know that, so I'm going to use the calculator. It's 1,002,001. And of course, a million squared is going to be 10 cubed squared, so 10 to the 6, or a million. And of course, this is easy to simplify. 1,001 minus 1,000 is just 1, so this is going to be plus 6. And let's see, we're left with a difference of 2,001 times 0.0003. Let me do that on the calculator. $30.015. Okay, so it costs us $36 to create the 1001st stuffed buffalo toy. Is that right? That seems off. Let's try that again. 0.0003 times 2001. Yeah, okay. 0.6003. So that means that it's going to cost about $6.60 to produce the 1001st stuffed buffalo toy after you've already produced 1,000 of them. Okay, next set of definitions. So these are terms that are used a lot in calculus to describe functions and features of functions. So we have this idea of increasing and decreasing, and then this idea of extreme points, or extrema, local maximums and local minimums. So a function is increasing on an interval if the function values increase as the inputs increase. So as the x values increases, the y values are also increasing. More formally, a function is increasing if f of b is greater than f of a for any input values a and b in the interval where b is greater than a. The average rate of change of an increasing function is always going to be positive. Now, a function is decreasing on an interval if the function values decrease as the inputs increase. Okay, so more formally, a function is decreasing if f of b is less than f of a for any input values a and b in the interval with b greater than a. And the average rate of change of a decreasing function is always going to be negative. Okay, now when you have functions that change from increasing to decreasing and vice versa, you get what we call local maxima and local minima. A local maximum is a point where a function changes from increasing to decreasing. Okay, so if a function is is going up, and then it starts going down, well, the point at the top is a local maximum. And if a function is going down but then starts increasing, that point in the middle is a local minimum. Okay. So we have a picture here. Yeah, the local maximum is just this point near the top of a hill, and a local minimum is just the lowest point in a valley of the function. Okay. Here's an exercise. Find the intervals where the function is increasing, decreasing, and state any local maximum or minimum values as ordered pairs. Okay, so it looks to me like the function is increasing from negative infinity up to -2. So here's an important thing too. When we talk about intervals where a function is increasing or decreasing, it really doesn't make sense to include the endpoint. So like, for example, this function at -2, is the function increasing or decreasing there? It's or staying the same? It doesn't make any sense to include the endpoint of an interval when discussing increasing or decreasing. So we always use open intervals with round parentheses. So this interval will be from negative infinity to -2, and we don't include the endpoints. The function is decreasing on the interval from -2 to positive infinity. And this function also has an extrema right here. So what is that point? That point, now this is not an interval, this is a coordinate pair, right? And that point has coordinates -2, 2. Okay, and this is a local maximum. Okay. Let's look at the next one. So here, this function seems to be increasing from negative infinity up to until we get to the point -1. And then it starts decreasing until we get to x equals 1. And then once x equals 1, it starts increasing again. And so our interval where the function is increasing is the union of these two intervals. And the function is decreasing in this region right here from -1 to +1. What about extrema? So this function has two extrema. It has a local max and a local min. So -1, 4, this is a local max. And the point 1, 0 is a local minimum. So when a function is a quadratic function, we can find its maximum or minimum. Remember, a quadratic function has a graph that is a parabola, and that parabola could open upwards and give us a local minimum, or it could open downwards and give us a local maximum. How do we find the local minimum or maximum of a parabola? We want to put the function, the quadratic function, into vertex form. How do we put that into vertex form? We complete the square. So let's review how we do that. So we're given this function. The profit in dollars when x picture frames are produced is given by the function p of x is equal to -4x squared plus 80x plus 2. This is a quadratic function. Its graph, because the leading coefficient of the quadratic term is negative, this will be a parabola that opens downward, and thus will have a local maximum. Find the number of picture frames which need to be produced to maximize profits. And what is the maximum profit? Okay, so we need to put this quadratic function into vertex form so we can find the vertex of this parabola. So recall, I'm going to rewrite the function When putting into vertex form, we need to start with a quadratic function where the coefficient of the squared term is 1. And the way we do this is we just factor whatever factor we have. So we factor the negative 4 out. And we factor it out of the first two terms. And we just leave the constant term alone by itself. Okay, now we have a quadratic function inside the parentheses, and importantly, the coefficient, if we just consider the function inside the parentheses, its coefficient is of the quadratic term is 1. So now we can complete the square. How do we complete the square? Well, we take the b value, which in this case is negative 20, we take half of that and square it, and then add it, and then subtract it. Okay, so our b here is negative 20. So b over 2 will be negative 10. So then b over 2 quantity squared is going to be 100. So we can rewrite this as negative 4 times x squared minus 20x. So we're going to add in 100. Whoops. Okay, but now I added 100 to the expression in parentheses, but everything in parentheses is being multiplied by negative 4. So really I added negative 400 to this expression. So to undo that, I add 400. Now we can factor this because it's a perfect square. And it will always factor to x plus b over 2 quantity squared. So what is my b over 2? It's negative 10. So x minus 10 quantity squared plus the 402. So this is my profit function. It's the exact same function as before. It's just written in a different form, which we call vertex form. So recall this form. It has this a times x minus h quantity squared plus k. And the vertex is equal to h comma k. So in this case, my vertex is going to be the point h comma k is going to be the point 10 comma 402. Notice in the pattern it's x minus h. So up above I have x minus 10, so my h is 10, not negative 10. So my h is 10, my k is 402. So h represents the x value where the maximum occurs. So at a production of 10 frames, our profit will be $402. We're measuring in dollars here. So we would say something like at 10 frames, profit equals $402. Okay? All right. A manufacturer found that the average cost, C, to produce X custom scooters can be found using the equation C of X is equal to 0.03x squared minus 4x plus 600. What is the minimum average cost per scooter, and how many scooters should be built in order to achieve this minimum? Well, one of the key things to notice here is that this cost function is quadratic. And whenever we have a quadratic function, we can either minimize it or maximize it, depending upon whether it opens upward or downward. Now, since the leading coefficient, or the coefficient of the x squared term of this function, is positive, this is a parabola that opens upward. Its graph is a parabola that opens upward. And so it'll have a valley, and so we can minimize this function. We can find the point that minimizes the cost, in other words. So how do we do that? Well, it's kind of a difficult function, so I think a good idea here would be to graph it first, and so we know what the answer is. So I've done that in Desmos. If you go to the website desmos.com, it's very easy to graph things. So over here on the left you see the function 0.03x squared minus 4x plus 600, and you can see it has a minimum when x is 66 2/3. Then the cost, the average cost per scooter will be $466 and about 67 cents. So now let's go back to our paper. So we know what the answer is already. It's going to be about 66 2/3, and then the cost will be 466 2/3. Okay, so let's keep track of that. That's important to remember. But now let's do this the algebraic way by completing the square. So c of x is equal to 0.03 x squared minus 4x plus 600. The first thing I want to do is I want to factor 0.03 out of the x squared term and the x term, or linear term. Okay, so I got to figure out, okay, 0.03 times what is going to give me -4? Well, what is 0.03? 0.03 is 3 over 100. So I need 100 over 3, a factor of 100 over 3 times -4 to get the correct value here. So that would be -400 over 3x. Okay, and you can just check. Yeah, if I distribute this 0.03 to both terms in here, of course I'm going to get 0.03x squared with the first term, and then when I distribute to the next term, I'm multiplying by 3 over 100, and I'm just going to be left with -4. So that checks out. Okay, so now I'm ready to complete the square. What is my b? My b is equal to -400 over 3. So my b over 2 will equal, I'm just going to be simplistic here and write -400 over 3 times 2, or 6. And then b over 2 squared is just that squared, right? So this becomes 0.03 times x squared minus 400. Let's fix that. Whoa. Minus 400 over 3 times x plus 400 over 6 quantity squared plus 600. And since I've added 0.03 times 400 over 6 quantity squared, I've got to subtract that off too. Okay, so it's kind of messy, but now we can factor. The point is that this expression is a perfect square. And you don't even have to think. It's always going to factor to x plus b over 2 quantity squared. But our b over 2 is negative here. So we're going to get 0.03 times x minus 400 over 6 quantity squared plus this 600 minus 0.03 times 400 over 6 quantity squared. All right, so this is our h. and this is K. 400 divided by 6 is 66 and 2/3. 400 divided by 6, yeah, 66 and 2/3. I'll let you check the other quantity there for K, but I'm sure if you compute that, you'll get 466 and 2/3. Okay, so the minimum average cost per scooter is $466.67, and the manufacturer should produce 67 scooters in order to achieve this minimum. So there we go. And that's it for section 1.3.